Hello everyone, you are here to go through our computer organization and architecture project titled Endianness Storage Visualizer. Computers deal with numbers every second, but how these numbers are stored in memory often remains a mystery. Our project brings that hidden process to life, transforming complex byte order concepts into something visual, interactive, and easy to grasp. I'll begin by walking you through what our project is all about and how it makes one of the toughest topics in COA both clear and fascinating. Our project overview. Our project explains how data bytes are arranged and stored in memory depending on the system's endianness, that is, whether it's big endian or little endian. We created an interactive visualizer that helps users see these differences clearly. Through this presentation, we will cover our problem statement, objectives, core concepts, system design, and finally, its practical application in real world. By the end of this session, you will see how this visualizer converts invisible memory operations into interactive, real-time learning experience. Introducing the dedicated trio who combined logic, design, and innovation to bring the Endianness storage visualizer to life. Arya Dash, the core developer, Arunya Rath, system developer, and Saloni Mohanty, UI UX developer and co-developer. Together, we transformed a complex memory concept into a clear, interactive, and learner-friendly visual experience. Introduction to Endianness. The Endianness Storage Visualizer is an innovative educational tool built to reveal what happens inside computer memory. It visually explains how the same number is stored differently in Big Endian and Little Endian systems. Why it's unique. Instead of reading theory, users see how bytes line up, turning abstract data storage concepts into an interactive visual story. Now, the problem statement. In computer organization, students often find it difficult to imagine how data is stored at the byte level inside the memory. The concept of endianness, which decides whether the most significant byte comes first or last, tends to remain abstract and confusing. Reading about it in textbook doesn't quite click until you can actually see it. So, we asked ourselves, what if we could make this invisible process visible? And that's exactly what we built, a tool where users can enter any number and instantly visualize how that same number looks both big Indian and little Indian layouts side by side with color coded clarity. Objectives of our project. Our objectives were very clear from the very beginning to visualize how data is stored differently in big and little Indian systems, to simplify the theoretical complexity of byte ordering through intuitive visuals, to make learning interactive, allowing users to experiment and learn in real time, to demonstrate real world relevance across networking hardware and system softwares. In essence, our goal was to take something technical, make it tangible, and turn learning into a visual experience.
Explaining the concept behind our Endianness visualizer. So, what is Endianness? It defines the order in which bytes are stored in memory. In Big Endian, the most significant byte, the big end, comes first. In Little Endian, it's the least significant byte. It may sound minor, but in computing, it can completely change how numbers are interpreted. Our visualizer makes this difference clear through color coded memory blocks, showing how the same number looks in both formats. Now imagine this. Two computers talking, one big endian, one little endian. If data is sent without conversion, what's 10 on one side might turn into something entirely different on the other. That's where byte swapping comes in. It rearranges bytes for consistency. For example, TCP and IP uses big endian, while Intel processors use little endian. Without conversion, they would never communicate correctly. Our visualizer helps users see this transformation, making a tricky concept simple and visual. Our system follows a clean modular flow: user input, conversion module, visualization engine, and output display. Input accepts decimal or hexadecimal numbers. Conversion breaks the number into bytes based on NDNS. Visualization displays colored blocks showing byte order, and output, that is, compare both formats side by side. This structure ensures clarity, scalability, readability, and a professional software like design. We use Python 3.x for development because of its simplicity and strong libraries. Key technologies will be Tkinter, used for GUI, NumPy for byte level operations, Matplotlib for the visualization. It runs smoothly on any system with 4 GB RAM and is compatible across Windows, Mac OS, and Linux, developed and in VS Code. Our system works through three core layers. Input layer handles and validates user data. Conversion layer performs byte swapping and logic. And visualization layer dynamically displays color-coded blocks. Together, they create a real-time interactive view of how memory stores data differently in big and little endian formats, turning a completely complex topic into a clear visual experience.
Major project modules. Our project is made up of 4 major modules, each playing a key role in building a complete system. Input module captures user data in decimal or hexadecimal format. Conversion module converts that data according to the selected endianness. Visualization module graphically displays every byte in the correct order. Comparison module shows big and little endian views side by side. This modular design keeps our system organized, efficient, and easy to expand. Now, core features and project identity. What makes our project unique is its educational identity. It's not just a program, it's a visual learning tool that transforms an abstract topic into an engaging experience. Through vivid and dynamic visuals, we help learners actually see how data is arranged in memory. The interface is simple, interactive, and perfect for students, teachers, and developers who want a clear understanding on endianness. Implementation and testing. We built the project using Python's tkinter framework, following a modular object-oriented approach. Each component was tested for correct input validation, accurate byte conversion, proper visualization, and smooth GUI performance. With continuous refinement, we achieved a stable and reliable output across different platforms. Results and output visualization. Our results met all expectations. Accurate byte representation, instant endianness toggling, and color coded memory blocks that simplify understanding. The interface is smooth and responsive, turning a challenging theory into a hands on visual experience. Real world applications. Endianness has real importance in computing. Networking. Protocols like TCP/IP use big endian for consistency. File systems determine how binary files are stored and read. Cross platform compatibility ensures smooth data exchange between Intel and ARM processors. Embedded systems helps interpret sensor data accurately. It's a fundamental concept every engineer must understand. Conclusion and future enhancements. To conclude our project, the Endianness Storage Visualizer bridges the gap between theory and practice. It transforms abstract ideas into clear visual learning experiences. In the future, we plan to add bit level animations, drag and drop input support, and hardware simulation modules to connect software with real devices.
Thanks for watching this video. Hit like, do comment and subscribe to our channel. See you in the next video.